So let's finish deriving the Clausius-Wilshire equations, at least the first one. The other ones, again, the procedure is very similar. Recall what we had, a chief satellite that at some point we said it's on a circular orbit. The LVLH coordinate system is defined as I radial, K normal to the plane, J completes a right-handed basis, and then we have a deputy which is close enough so that we can realize its motion with respect to RC. So in other words, we want to find a way to represent how the vector ρ behaves in that basis, where we have called its projections x, y, and z. And we did get to this point, having assumed that the chief is in circular orbit. We add this differential equation. Let's see, RC plus x, and on the right we have minus mu over RD cubed RC plus x. Okay. The second one was y double dot plus 2 omega x dot minus omega squared y equals same minus mu RD cubed. There is only a y here. And then the last one is z double dot equals minus mu over RD cubed z. So these would be my equations for how x, y, and z evolve if this object is in circular orbit, and I assume Keplerian only type of gravitational attraction, nothing else. So it's nonlinear because of this expression on the right. And so what we did is, this was the page, we said, okay, let's linearize the first one. So these are the pieces that I have to linearize, all the right-hand sides. And we did just the first one. So if we call this first one the f1 of x, y, and z, we have to deal with this function. So basically, let's just say that f1 is this. The minus mu, I don't really care. I don't have to do anything about it. So I'll focus on that. And you can rewrite it as we did last time as rx plus rc plus x divided by rc cubed 1 plus 2x over rc plus x squared plus y squared plus z squared over rc squared, and this is at the 3 over 2. Okay. And so we linearize this function. The first thing you do is you compute it at the linearization point. And I hope we have agreed that the linearization point is 0, 0, 0, right? If the deputy collapses to the chief and he sits on the chief all the time, has the same orbit. So I want to just see how the perturbation with respect to that condition, which is called the chief, behaves if I'm not going too far from it. And so if I plug all zeros here, we said that this is going to be, well, 1 over RC squared, right? Because this goes to 0, this whole thing becomes a 1 over RC squared, and we'll leave it there. And then I have to compute the partial of this f1 function with respect to x, because I'm looking at the first one. In, again, 0, 0, 0. And so you do, I think we did this. Derivative of the numerator, which gives you a 1 with respect to x again, times the denominator. So this is just as it is. I'm not going to rewrite everything that it's in parentheses. Okay? Then you subtract the numerator as it is, that multiplies the derivative, the partial of the denominator, which is, let's be careful here, RC cubed, then I have a 3 over 2, 3 over 2 minus 1 gives me a square root, so I have the parentheses again, this time is at the, it's just under square root, 1 over 2, and then I take the partials here where I see x, so I'm multiplying these times 2 over RC plus 2x over RC squared, and I'm not done. This whole thing has to be divided by the denominator squared, which is RC to the 6th power, and this becomes whatever it's in the parentheses to the 3rd power. Agree? Any steps not clear? Just taking the partials. And this is just the partial with respect to x. I haven't substituted any zeros yet. Okay? Well then, if you do substitute the zeros, a lot of stuff goes away. All the parentheses becomes ones, right? So I have, let's see what I have. I have RC cubed times 1 minus RC plus 0, it's RC. Another RC cubed, the 3 over 2. The parenthesis becomes a 1. And here I only see, in this last parenthesis here, I only retain 2 over RC, right? X goes to 0. And down here, I only really have RC sixth. Make sense? And let's see what simplifies here. This goes away. This is to the 4th, to the 3rd. So 1 minus 3. I have a minus 2 RC third power over RC sixth. So I have minus 2 over RC third. So the third power, right? That is what I have. And so my approximation of F1, at least the piece that I'm doing, I'm not going to do the partials with respect to y and z, okay? I'm only going to care about basically this component, F1, 0, 0, 0, plus the partial of F1 with respect to x in 0, 0, 0, that is multiplying x. Is it clear what I'm doing here? You can say no. That means yes. Okay. Let's see. Well, this is pretty much done for us. It's 1 over RC squared. And let me rewrite this as RC over RC cubed, just because I have a cube there. And then this thing, this partial here, it's right here. So I have minus 2 over RC cubed x. And so if you want to rewrite this in a different way, let's see, you get RC minus 2x over RC cubed. What was that? Did I miss anything? Did I forget any minuses? I may have. I may have wrong notes as well. I know what I have to get. You know, that's fine. That's what it is. Remember, there is a minus mu in front of it. So if I go back here to this equation, can I erase this sketch? And I substitute what I have. The first one is going to look like x double dot minus 2 omega y dot minus omega squared RC plus x. And this has been approximated to, what do I have? Minus mu over RC cubed, that it's multiplying RC minus 2x. You like that? How did I put this in there? So that is my approximation right there of everything except the minus mu. So I linearized this ugly function and it became that one. Remember, RC is a constant. It is a circular orbit. So I just put back the minus mu that I didn't consider because I didn't want to carry it around. This actually has a specific meaning. This is omega squared. Right? Go back to your circular velocity. What is the circular velocity? It's square root of mu over RC. So you need a 1 over RC in front of this to get the angular velocity that goes inside and becomes RC cubed. Anyways, that's omega squared. And we like that because it's going to simplify a lot of stuff. So if I go one more step, x double dot minus 2 omega y dot minus omega squared RC plus x. I have here minus omega squared RC. I like that. And then plus omega squared 2x. And these guys go away. And my final equation is what it needs to be. I hope it does. Let's see, what do I have? Minus omega squared and another, well, 2 here, so it becomes a minus there. So it's minus 3 omega squared x equals 0, which is the first of the Cauchy-Wilshire equations. If you go back to the equations I gave you last time at the beginning without even knowing what they were, that's the first one. And you can follow the same procedure for the other ones and get the remaining of them, which I'm going to rewrite here just to summarize. Okay? So I hope the procedure to get these is clear. You linearize the dynamics of the deputy with respect to a chief satellite that you picked as your reference for linearization. And you assume also a few things, that it's in circular orbit, mainly. And so you can find these equations. If you solve for them, which we can do, they will give you the evolution in time of x, y, and z, right? I mean, the first thing you can do is just grab them and integrate them numerically. And remember, omega is the square root of mu over RC cubed. All we need to know is that that's what it is, and it's constant. We like constants in front of variables. Yep, there's something missing here. Yeah. Okay. Any questions so far? Can I move on? So this, last time though, what we did is we took this system as an example and we said I can rewrite it this way, right? So now, when you're looking at these equations, remember you are sitting on the chief satellite and you are looking in the LVLH directions. X, or the I direction, K, which is the normal to the plane, and the J direction, right? And so this little vector that goes from the chief to the satellite, the other satellite, is projecting on these three axes, right? That's really what we have. The projections of ρ behave like that. And we said we can put it all together in this form. I do have the matrix. I'm actually going to pull up MATLAB in a little while, so I don't need to rewrite it here. Now, if you have taken classes where this is, explained, and you know that this is a matrix of constants, we said that this is a 6 by 6 matrix, right? Constants. There's nothing changing in there. This has an analytical solution. You can solve this. You don't need to do it numerically. And that's the first beautiful thing of getting these equations, because you don't really have that luxury if you just go with the full-blown nonlinear dynamics for chief and deputy and then subtract the two vectors. And yeah, you can do that, but it doesn't allow you to get any analytical solution, which is pretty useful. Do you know how this is solved? Any ideas? Any memories? You don't need to prove how these equations are solved. This is assumed to be known at this point. But somewhere back in time, there was a class, right, where they did that. No? Never? Differential equations? So, does this sound familiar? X of t can be expressed as the exponential of the matrix A times t that multiplies the initial conditions for x, where this scary thing, which is the exponential of a matrix, there are procedures to compute it. The formal, I never remember that because no one really solves it that way, but the formal definition of it, it's this one. But again, there are procedures to compute this. This can be computed in closed form. It will be summation for k that goes from 0 to infinity in principle, 1 over factorial k a t to the kth power, where you need to remember that for k equals 0, you basically substitute in there just the identity matrix. Sounds familiar? Exponential of a matrix? There are procedures in MATLAB does it for you, and that's exactly what I'm going to do next, as soon as we're done with this. But that's great. You can tell me, and that will be the topic for next class probably. If you tell me what is the initial state for x, so in other words, if you know where the deputy is with respect to the chief in this form, right, because that's really what we have. This is my state vector. Remember what we did last time. If you have the initial conditions for those equations, you don't have to integrate them. This will transform itself into a matrix, which is a function of time. So you just have initial condition, a certain time, I can tell you where the state is. I can tell you x, y, z, x dot, y dot, z dot, exactly, without having to integrate from 0 to that time, right? So the way this is usually found in literature, it's expressed this way. Once you compute that exponential, which I'm going to do in MATLAB, x of t is basically expressed as a transition matrix, state transition matrix, that's what it's called, phi of t times x0. So this is going to be another 6 by 6 matrix, function of time. It's called state transition matrix, okay? And it can be found in analytical form. One more thing I want to do is split that matrix in sub-matrices, because it will be useful when we talk about maneuvers. So if x of t is really this matrix that multiplies my initial state vector, I can see these split the following way. Let's see. 4 sub-matrices. Is it 4? Yeah. So my state vector is 6 components, right? The first 3 are, I don't know how I want to call it. It's basically a row. It has to do with the position, right? They have to do with position. Actually, let me just call it little r, just like that. And these are the velocity components. Basically, they don't have time derivatives. These have time derivatives. And so on the other side as well, I can do the same. I can say that x of t is the same as the first 3 components that have to do with the position, and the last 3 have to do with the velocity. So you can split these into a first piece, which is phi. What do we want to call that? That maps positions into positions, r. And then here I would have terms that map positions with velocity, right? And down here I would have, let's see, velocity with positions, dr, and transition matrix, sub-matrix that connects velocities with velocities. Basically what happens is that this is a 6 by 6 matrix. You're gonna get this 3 by 3 piece here, and everything that is in here, it's only going to multiply positions. So that's why I call it phi rr, because on the other side I get only the first 3 components of the state vector at a given time related to the initial state vector, only the positions. And then this other one is going to give me the contribution of the initial velocity to give me still the position component of the state vector. Is this clear? I can try to explain it a little better. But if I break it really into 1 by 1 components, that's really what I'm doing here. Let's see. Okay, so this is my x at any time t, and then I'm just taking this matrix here, which is 6 by 6, and I just imagine that I divide it this way. And here I have something like this, except it's a time 0. And so here it should be a little clearer that these 3 guys are given by multiplying this submatrix times these first 3 components plus this submatrix times these 3 components. That's why I call them that way, right? All right. I don't know if I want to open MATLAB yet. Probably not. Let me actually finish this. So let's assume that phi is given, right? I'll show you how you basically can compute it in MATLAB. It's really not that big of a deal. But let's say that we know it, whatever it is. So my my position at a certain time t, so if I take basically only the first 3 right there, if I spell it out like this, is going to look like what? It's going to look like the phi matrix, submatrix RR that multiplies my initial position. Now you're probably thinking, where is he going with this? I'll tell you in a second. RV that multiplies my initial velocity. Okay? So, say that, since we're talking about proximity operations and maybe a cargo that is going to the International Space Station, or in the past the shuttle that will go to the International Space Station, everything on this side is known, kind of, right? What can I do with this equation? What would be my goal if I want to reach the chief? What do I want to happen here, somewhere on these variables? When you are at the chief, what are your variables? Your state vector, what is that? Everything is 0, right? Hopefully you don't have any relative velocity, because you can be at 0, 0, 0, still have some residual velocity, so you're going through the chief. That's not a good idea. But say that I want this to be 0. I can do that. 0, 0, 0. It's equal to this. All right? But this is where I am. Really can't do much about it. What can you do with this? So say that at a certain time that you call time 0, we decide when you know, to say this is time 0. Say that I have this position and this velocity with respect to the chief, okay? But I really don't like that. I want to go at 0. I want to drive my position to 0 to begin with. Position, I mean, it's what it is. What have we done that assumes no changes in position but only in velocity? Impulsive maneuvers. How about, instead of accepting that this is my velocity, I exert an impulse and I change it so that this is satisfied. So this will be my real initial velocity, but I'm going to apply an impulse that changes that into whatever is needed so that I can go straight to 0. So this is basically a two-impulse maneuver. The first one will modify this velocity and satisfy this equation so that you go to 0, but then you probably reach 0 with some residual velocity, so you have to cancel that. So the second impulse is whatever is your velocity when you reach 0, just kill it. Just burn in the opposite direction. Yes?
So how do you avoid this diffraction?
Well, you probably don't want to go exactly on the chief, maybe a few meters before that, and that's exactly what the shuttle would do. They would do a burn and not. So basically what you do is you do it step by step. Instead of saying I want to target 0 right away, I'm going to target, this is x, this is radial. So maybe if you want to approach something, you will do it in the direction of y. So say I'm going to target 0, I don't know, 10 meters, 0. You do it step by step. You can do that as well. I can stick any other numbers here and still compute what is the velocity, as I'll do in a second. That basically changing my velocity right now will just have me coasting exactly to that final position. That's exactly what I'm trying to do. As you've done with Hohmann maneuvers, what you have done is you have burned us at one point, then you go to a different trajectory, you just wait, you don't do anything until you are at the right point, and you burn again. And this is the same principle here. It's just done in the LVLH coordinate system, in a relative motion framework, but it's the same idea. I change my velocity now because I don't like it, I want to be somewhere else, and that somewhere else, for example, could be 0. So this would be a rendezvous maneuver, right? So how do you solve for that? Well, it's pretty simple, right? This is all zeros. So my, let's just call it x dot star, y dot 0 star. So this would be the velocity that I actually need to have to go to 0. So this would be star here, star here, star here. Well, it's going to be equal to minus phi RR of x0, y0, z0, inverse of that. What is that, RV? So that is the velocity that you should have. So the delta V here, at least in LVLH for now, I need to spend a few words on this, is going to be basically the x dot star, y dot 0 star, and the same for z, minus what you actually had, right? That is your required change of velocity, so that instead of being at this relative velocity, you go to this one, and you're actually going to reach 0. And again, you're going to reach 0 with some residual velocity, so if you really want to stop there, you will have to correct for that. That's really not a big deal. Is it clear? So just to explain why we go through this pain of inverting matrices, which, by the way, again, I'll show you, they can be computed once and for all analytically, is because if you want to do this in the inertial frame, imagine doing that. I just give you two random satellites that are kind of close to each other, and you have to figure out a two-impulse maneuver to go from where the deputy is to the chief. It's not going to be that simple, and not that analytical, probably. You can try. But this is using linear theory, which is very nice. Very convenient. Is this clear? So I'm just trying to reproduce what we have done for regular inertial orbits, just redo the same for a relative orbit, LVLH. One more thing before I open MATLAB and show you examples of how this analytical solution looks like, what we can do with it, how we can implement that maneuver. What would be in practice, because everything is now done in the relative coordinate systems, right? Everything is done in LVLH here. But if, well, in real world, what you have to do with your deputy to obtain that delta V, how would you tell me what delta V I have to apply in ECI? What do you think? Because these are all relative coordinates. That's in LVLH. How you transform these to an actual maneuver that you have to apply there? What do you think? Okay, so what is the velocity of the deputy? It's the velocity of the chief plus the relative velocity, and this thing is, if you want, you can express it this way, right? It's exactly what we've been playing with, these coordinates here. I'm sorry, what am I writing here? Y dot j, z dot k, right? This is the relative velocity, plus the angular velocity of LVLH, ECI, cross with rho. This is transport theorem, right? Okay. Well, then I can write two identical expressions for before and after the burn, right? I can do that. What is changing before and after the burn? If it's an impulsive maneuver, which of these variables has to change, and which ones we assume they don't change because it's impulsive? I'm sorry? VREL has to change. And as a consequence, VD probably has to change. Is the chief going to be affected by the fact that the deputy is firing around thrusters like crazy? Chief doesn't care, he's just going on its circular orbit, looking at this crazy guy firing thrusters, right? This is not going to change, it's not affected at all. And the same for the angular velocity of the chief with respect to ECI, of the LVLH, right? And since it's impulsive, my position is not going to change. So in other words, if I write two expressions like these and subtract them, I'm going to see that V of the deputy before the, let's put it this way, after the impulse, minus V of the deputy before the impulse, it's VREL after minus V deputy, well, I'm sorry, VREL before. All these terms don't change, so they basically get removed. But you have to prove it that way, by the assumption that it's impulsive. Does it make sense? And this is beautiful, because you can basically take the exactly that. This would be this vector, except here I don't have the basis, but that's the idea. It's the after and before the impulse. Subtract, just work with the x dot, y dot, z dot in LVLH, and that is giving you the impulse. Now, a different story, if you want to project this vector into ECI, you have to, transform it, but you may not need to. All right. I want to convince you that these equations are really cool, and you can do a lot of stuff with them, because I think if you just look at the board, it's not very convincing. So I'm going to go through the steps that we have seen in MATLAB. Some of this is symbolic MATLAB. I will post these. So these are all declarations of symbolic variables that I just decided to use along the way. nothing major. Okay, so this is my A matrix, right? Exactly the one that we have found last time. Is omega, and it's at this point of my software, it's only a symbolic variable. So in other words, if I run my code up to this point, hopefully it runs, yes, A will show It's not going to show a number, okay? Symbolic calculation. And then I'm going to actually write that x of t, that's the idea, is exactly what I told you. It's the exponential matrix of at times x0, which is a symbolic variable. I just always have a simplified instruction so that hopefully MATLAB can clean my solution. And that is what I get. These are the solutions, closed form solutions for Cloyce-Wilshire equations that I invite you to get from your book because they will look a little nicer than MATLAB. I think you can. I sometimes do this. It doesn't necessarily make it prettier, but you can do this. It's not too bad. It's a little better. Have you ever seen this command? Yeah, I discovered it a couple of years ago, and then I decided that it was kind of pointless because it doesn't really help. Because it decides to move stuff around. That number 1 is a cosine of omega t minus 1, and for some reason it's not showing. It's just down here. So it doesn't make my reading of the equations that much better. So I don't know if I want to look at it this form. But the bottom line is you have them in the book. Look at them. I'm going to comment a little bit about them. The first thing you notice is, as expected, so just look at the first three. The first three will be x of time, y of time, z of time. Again, those are functions of time. Once you give me, there will be x zeros, y zeros, and the initial conditions all over the place, but those are constants, are given. So you give me a time, you input it there, and you know the position and velocity in VLH. So let's look at the first three. The third one, z0, cosine omega t, etc., as you can see, has nothing to do with the first two. It's completely independent. It goes by itself. It doesn't care. The out-of-plane motion in this approximation of relative motion that we have is decoupled from the in-plane motion. And by out-of-plane, I mean the z direction, right? In-plane is x and y, the radial and tangential. And what is the out-of-plane motion is really just an oscillation. It doesn't matter that you have a cosine of omega t and a sine of omega t and a bunch of constants. When you sum together sines and cosines, trigonometric functions with the same period, you basically get a sine type of behavior. That's what you get. There are no other frequencies involved here other than omega. So that's pretty nice. It's an oscillator. It's an undamped continuous oscillation of fixed amplitude. That's what it is. The other two are coupled as expected. The one thing you notice is the first one doesn't have any other function of time other than sines, cosines, nothing else. The second one does. Maybe I should go there with the mouse, and it will be a little clearer. There is sine here, but then look at this. There is a linear term with time. So something is drifting with time. That term, it's a constant times t. As time goes by, your y, remember that's the equation for y as a function of time, it's going to continuously go one direction. At least that term does that. And the same with this term, right? The other ones are sines and cosines, so they are periodic functions, but these two are not. And so what is actually happening, which is physically expected, is that there may be a drift of the deputy with respect to the chief, depending on their original orbits. And let's just say that this is looking at above the orbit, and this is the Earth, and this is where the chief is. So, and this is its circular orbit. Just intuitively speaking, if I have a deputy which is right on top of the chief, right here, at some given time, and it's moving on a higher orbit, even if it's circular. Let's just say it's circular. There are just two circular orbits. The deputy has a little bit more height. That's all. And remember that LVLH is going with the chief, and this would be your y direction, right? The j. If the orbit is flying this way, it's moving that way. What do you expect? You're sitting with the chief. What do you expect the y of this to do? The deputy is moving faster or slower?
Faster.
Higher orbit. higher orbit. It's moving slower, right? The orbital period goes with the same major axis. It takes longer to do one rotation, right? So this is, from this guy's point of view, it's drifting that way. Reverse the situation, the deputy is below, down here. It's actually going faster. So from this guy's perspective, he's actually falling behind, the deputy is going forward. So that is why, in general, you do have, and I'm simplifying here with circular orbits just to get the point across, right? I'm really simplifying the case because these two orbits could have eccentricities. Well, not the chief, because that's my assumption, but the deputy can have an eccentricity. But that justifies why the y direction can have a term that does increase with time. Other than an oscillation, it does increase with time. It goes one way or the other because you may be higher or lower. In other words, the deputy could have a same major axis that is greater than the chief, or vice versa, and depending on this, you get a drift in one direction or the other. So if you're trying to dock with that, you better stop that drift, right? For example, that's a problem. Forget for a second that those terms are there. If I remove those terms, what do you expect, just by intuition, if you have two functions of time that are basically a bunch of sines and cosines with the same frequency, the x and the y, that's what they are, right? But they are coupled. What do you expect the shape of the orbit to be in the plane? And by orbit, I mean relative orbit now. So if this is the I direction, this is the j. I know it's kind of unconventional to do it this way, but that's how I did it. So in this LVLH basis, forget about the drift, the term that is function linear with time. If I only have sines and cosines, what do you get? X behaves like a cosine, say for example, something like this. X of t is, I don't know, x0 cosine of omega t. I'm oversimplifying here. Y of t is another constant sine of omega t. If these were the same, you would expect a circle, right? Those are, in general, not the same. So in general, if you remove the drifting part, you can get ellipses. If you remove the drifting part, okay? Because you just have sines and cosines in both solutions except their amplitudes. That's what you get. Now, if I put together the drifting part and the ellipse, say that you're drifting, I don't know, that way, you may get motions that look like this. It's an ellipse whose center is drifting away. I invite you to look at these analytical solutions a little more closely and just play with them, because that's basically what you get. I do have a paper, by the way, on my website. If you want to dig into more details, I'll show it to you in 1 second, for those who are interested. That does go through showing, with a few steps, it's really just the beginning of this paper, that there is it's really beyond what we have to do here. But this is paper, what, number 19. This one here, at the beginning, so forget about all the guidance part there, but at the beginning we do a simple substitution of variable that clearly shows that you have an ellipse, an elliptical motion, and you superimpose on that just a drifting motion, and that's what you get. So that is done commonly. But let's continue here. Let's run this thing, because I'm going to show you a plot. Of course. These are the same matrices that we discussed before. The phi is the entire state transition matrix. Then I break it into little pieces in case I want to do that rendezvous maneuver. This would be the new velocity that you need if you want to rendezvous. Exactly that formula I wrote down here, minus the inverse of phi RV, phi RR that multiplies the initial condition in case I want to do that. But I don't think that's the first case I'm running here. And then I decide, okay, let's try just some numerical cases. So I randomly, with some knowledge about what these numbers should be, we'll talk about those next time probably. Because here I'm just picking initial conditions for those equations in LVLH. That is not usually what you do. You have two satellites that are flying their own orbits. You have to figure out from those orbits what those initial conditions are. You don't get, in general, you don't get to just pick x, y, z, x dot, y dot, z dot. You have to compute them. And you can start thinking about how that's done. It's really not that big of a deal. But here I'm just choosing them because I'm going to integrate the classical-Schreier equations directly. Okay, so if I do it in two different ways. Here I have the analytical solution, this bunch of formulas, the same ones I showed you before. Now I actually have numbers for them. And the vector t is vector of times that goes from 0 to, I think I chose 5 orbital periods for the chief. And anyways, I'm not doing any ODE 45. And I plot that. Let me see what I'm plotting here. I don't remember exactly. And then I do it with ODE 45. Yep. Okay. So these are just random conditions that I picked. That's the radial direction x of LVLH. This is the tangential direction this way. That's the outer plane. And that it's a 3D plot that I can, this is my start point here that I gave, and this is where the simulation ends. If you go and look at, of course it doesn't want to work, well this, and look at the plane, x and y, that's the type of motion that I was talking about. It's, if you somehow remove the drift from the picture, you will get a continuous ellipse. But this ellipse is actually moving because there is that t term, that linear term with time. So that's the projection in the xy plane. Let's see, what do we want to see? Well, we can see all the planes here. The oscillation outer plane, it's always the same. That's why you get a closed type of figure. And this is what you get in the other direction. Okay. Now, this is all nice, but in reality you don't want to see this, right? Drifting away, why are you doing proximity maneuvers? And by the way, I can run this until the end, just show you that if I then take the classical-Schreier equations and actually integrate them with ODE 45, I do get the same thing as expected. So if I go back to my 3D view here, I think the blue or the black is just overlapping the other solution. The analytical solution and the numerical one are the same, they better be. Now, how do you prevent this from happening? Again, this is just drifting away. So if the satellites were friends at some point, they're not friends anymore. They're just, you know, this is what, kilometers. After, I don't know, 5 periods, the deputy is 1,200 kilometers away. That you really don't want to call that proximity operations anymore. Well, what about I take my nice, pretty, after the pretty command here, solution, and I remove that. There is a case where you can remove the drift. If you put your satellite in a specific state, relative state, you can avoid that drift. And how do we do that? Well, I'm going to take everything that has a linear term in time there and just try to make it disappear. So what do I have? I see an x0 minus 6x0 omega t, right? Should I highlight that? This one? I'm sorry, this one here, right? Yep, minus the x0 is outside the parentheses. And then the only other t term that I see is this one, which is actually a y dot minus y dot 0 minus 3 y dot 0 t. T because omega, and it's divided by omega, so omega goes away. That's what I have. Now this is all the drifting part. This thing is what causes you to drift. You can rewrite these as minus 6 omega x0 minus 3 y0 dot t, right? That's everything that has a linear term. That is the only component that it's increasing with time or decreasing with time. It's drifting away. Make sense? So how about I look at the coefficient for t and I make it 0? I can do that. If you can, with your maneuver, make this 0. In other words, for example, the velocity at time 0 is equal to minus twice omega x0. You're not going to see that drift anymore. Right? Let's try it. I have that exactly up there. Here it is. I'm going to give you this software, by the way. So that is exactly that formula, minus 2 omega x0, 5 orbital periods. Here you go. No drift anymore. You just keep going around the ISS, for example. Whatever that is, you get a closed orbit like this. Yes?
What do you have to physically do to
Maneuver, correct the velocity, for example. So if your velocity is say you are in a certain configuration, x0, y0, z0. You call 0 anytime that you decide. It's when you're going to maneuver, for example. And you know that you're here. Your velocity is probably not satisfying this relationship. Well, then you apply an impulse that leads your second component of the velocity to be this. Impulsive maneuvers are nice for that reason. I'm going to change my velocity right now and do whatever I want. That's the idea. Yes? Sorry? Well, yeah, of course. This is going to change. So everything we're seeing here is, imagine that the deputy is doing maneuvering, the chief is just sitting there and going around in a circular orbit. So of course you're modifying the orbit of the chief. In other words, what is actually happening, and we'll elaborate more next time, is that when you have a drift, this is in practice what it's happening, is that the same major axis of the deputy and of the chief are not the same. If this happens, there is drift. Why? Because the orbital periods are different. If you have two orbits, even if one is circular, the chief's one, and the other one is eccentric, but they have the same semi-major axis, their periods are going to be the same. And if you have two physical phenomena that have the same period, well, you will see the relative motion repeating itself. You get that. So you get that only, basically, a non-drifting orbit if that is actually true. Well, not that, this is true. And so what you are, that's a good question. What you are actually doing, you're changing the deputy's orbit so that it has the same major axis like the chief. But it's just that I'm doing it, I don't see the maneuver done this way because I decided to move to LVLH, which makes my solutions analytical. I can manipulate here because doing that in ECI, I mean, it's doable, but why not using linear solutions? They're very, very convenient. Yeah, make sense? And then I have a few more minutes. I have another case here. What about we do the rendezvous maneuver now? I don't know if I want to do 5 orbital periods. Yeah, maybe. So if I uncomment this, oops. This is just going to tweak my initial velocity so that is exactly what comes out of this solution here. Again, it's just the first impulse. The correct initial velocity so that your trajectory goes to 0. Okay? And so hopefully this works. Let me see. Yeah, well, it is going to 0, but that's kind of not fun at all. Let me go back to the velocity that I had before, because this was already in a closed orbit. 0, 1. This is a lot more entertaining, probably.
How did you say you solved for the drift velocity?
I'm sorry, say it again.
How do you solve for that drift velocity without just punching
The drift velocity. Oh, this, what velocity? This one?
No, the point you put in.
I just made them up.
How did you said that normally you actually have to solve.
Yeah, we'll do it next time. So I will start from the actual chief state vector in ECI, deputy state vector in ECI, and you subtract the two, project into LVLH, that gives you x, y, z. Yeah, apply the transport theorem to figure out x dot, y dot, z dot. So that's how you should do it. These I just made them up. You know, I don't think this is, for some reason, these are not the combination of numbers I had that made, I have an orbit in mind that looked a lot nicer than these. Yeah, this one. I think it looks cool. Anyways, you're starting from this point, right? And I said the velocity now, it's the right one to go to 0. And I expect the green point to be at 0, 0, and that's what it is. This is the, what is it, the XY projection. So, in other words, I was sitting here with my spacecraft. I had some initial velocity that wasn't going to lead me to do this. I fixed that. I changed that velocity so that the trajectory, it's actually ending up here. And here, if I continue the simulation, this will go away because I haven't corrected the velocity. But there, whatever is your residual velocity, x dot, y dot, z dot, you just have to completely erase that. Just apply an impulse which is exactly equal and opposite to that. And in that case, you will sit there, because the solution for quasi-Schwarzschild equation, everything 0, is a solution. It's an equilibrium point. If you take those equations that I don't have anymore, those differential equations, and you plug in 0 everywhere for positions and velocities, you get 0 equals 0. It's a solution. So if you sit at the chief with no relative velocity, you're going to stay there, which is the idea of rendezvous. Yes?
This is a picture of what the spacecraft is actually doing.
Yeah, it's starting, seen by the chief. The chief is sitting right here. This is a relative trajectory, okay? I am sitting here with the chief. This is my, it's the other way. This is my radial direction, and this is my direction of flight of the chief. The other guy started there, the deputy started there, and has the right velocity with respect to the chief, so that it's just following this path, doing nothing, just waiting, and it will eventually hit the chief. And I say hit because if I don't correct that velocity, it's going through it. So in practice, you probably want to pick a point here. Well, these are kilometers, not there, but not exactly at 0. But the procedure is the same. Yes?
So have you seen the movie Gravity?
Yeah.
So in the movie Gravity, when they were trying to use their little thrusters to get to the
These are small corrections. These are small corrections. I have no idea if that's even feasible.
So it's not that simple. Like I have to go into a different orbit or something to catch up with.
There is one.
I can't just...
Yeah, there is one thing that we're not doing here. It's attitude dynamics, because everything is a point for us. Just imagine that you have to point some kind of physical nozzle in one direction to give you exactly the correction of velocity that you want. And I can't imagine a human being flying in space to have that kind of capability of, oh yeah, that's the X, the Y, the Z. Yeah, good luck doing that. I don't know how you can do that. It's it's science fiction, but I mean, you have to have some pretty cool sensors to tell you which way to go. Yeah.
Why is it doing this in this shape? Or is that just two impulses?
It's still the same type of motion, that it's a 2. So if I continued here, this will repeat itself. It's that ellipse that drifts away. That's exactly what it is. The only thing that I have basically done here is I made sure that that velocity there is such that this drifting ellipse is going to go through this point. That's really what I've done. I'll post this software and you can play with it. And maybe I should take question at office hours or right after this, because it's 51. Oh.
Are there more efficient ways of doing it than like drifting that way?
Oh yeah, I mean, you can. Faster ways, yeah, oh yeah. So that's a good question. So notice what I've done here. I have decided what is the final time. I am deciding how long this is taking. So I can actually make it quicker. I can make half an orbital period or even just another time. It will still go there in a shorter trajectory. It's taking less time, but it's going to cost you more. So play with this. That's a good point. Play with this. Change some of the parameters, the time that it takes. If you have the luxury of waiting several orbits, the cost in delta V is going to be much less. Yep. Okay, I'll see you Friday.